should be good now. Okay, hello everybody. Thank you for joining us for Astronomy on Tap Köln. We are excited for this event today. So please sit back, relax, grab a drink, and enjoy all the knowledge that we're talking about and the discussion that will follow. Today we're joined by Dr. Brandt Gaches. Brandt has completed his PhD in 2019 at the University of Massachusetts, studying under Dr. Stella Offner, and he was looking at stellar feedback in molecular clouds. For the last 2 years of his PhD, he was also a member of the University of Texas. And then in 2019, he started at the University of Köln as a postdoc in the group of Professor Steffi Balch. And he's also been an affiliate member of the Center for Planetary Systems Habitability at the University of Texas since 2019. He's also made presentations for Astronomy on Tap in the past, but at a different satellite in US. But we are excited to have him. His research interests include astrochemistry, cosmic rays, protostellar feedback, and short-lived radioactive nuclei. A lot of different things, but today he will speak to us about astrochemistry. So Brandt, thank you very much for joining us.
Yeah, thank you very much for allowing me to give a talk here. As Craig said, I've given talks at other Astronomy on Taps, and this is the first one I've given virtually, so it'll be exciting and interesting to see how this happens. So yeah, today I'm talking about astrochemistry, and in particular from kind of simple molecules like carbon monoxide up to life-bringing chemistry. So in particular, I'm going to talk about why should we care about molecules in space, and also how do we observe them, and I'll talk a little bit also about how, as a theorist like myself, we model the chemistry in space. So to start with, let's look about why we should care about molecules. This is a optical and near-infrared image of Barnard 68, which is kind of...
Sorry, you're not sharing anything right now.
Oh my God, I am so sorry.
My apologies.
As I said, first one virtually, so that was okay. So
now we see it.
There we go. It definitely helps to give a presentation with the slides. So why should we care about molecules and how do we observe them? So this is the optical and near-infrared image of Barnard 68, which is kind of held to be the prototypical Bott globule. It was first observed and added to Barnard's catalog in 1919. And what they basically saw was this appeared to be this big empty space in space where there were no stars. And it was soon kind of figured out that this is because the gas is so cold and so dense that the dust, which is in the cloud, obscures all the optical and ultraviolet light behind it. And so this was before the first detections of molecules, and so there was a lot of people trying to figure out exactly what was causing this or what the properties of these dark objects were, although it was pretty clear early on that it wasn't like, this thing was actually a void in space. That was kind of held to be not favored pretty quickly. And so they pretty quickly thought that this just must be a cold blob of gas. And we see these things kind of all over the place, these kind of dark lanes. So this shows both an optical on the bottom and a near-infrared image on top towards the Milky Way center across the plane. And if you look in the optical, maybe if you squint your eyes, you can see some kind of dark lanes in there. But in particular, in the near-infrared, you see a lot of these dark lanes. The near-infrared allows you to see some of the other stars. It's also a very deep image, and you see all these dark lanes streaking across it. And these appear basically anywhere you look in the galaxy. Within the plane, if you look at other galaxies in optical or ultraviolet, you see these dark lanes. But the moment you look at it at long wavelengths, so in this case, you're looking at the emission from cold dust. So this is very long wavelength thermal emission. All of this gas all of a sudden lights up like very brightly. And this was, again, kind of a signpost that what we're seeing is very cold, dense gas. And we can detect it very easy with the thermal emission from this cold dust. But the thermal emission really only tells us how much is there, and it doesn't give us any information about the dynamics or the motions of the gas that are within all of these clouds. And again, we see this is another kind of very zoomed in image of a dark lane that's actually pretty close to us. This is part of the Taurus cloud. And again, if you then superimpose the long wavelength radio emission on top of it, this dark lane all of a sudden becomes very bright, and you see that it's this long filamentary structure with maybe a couple bright things in there as well. So very early on, before we had any detections of molecules, some theorists and other prominent astronomers tried to tackle what the properties of this gas were, and using the data that they had at the time, some of them, even some of the most prominent astronomers at the time, made some pretty wrong predictions. So Sir Arthur Eddington, for instance, said in 1926, this was a decade before the first detection of any molecules, said that it is difficult to admit the existence of molecules in interstellar space, because when once a molecule becomes dissociated, there seems no chance of the atoms joining up again. And this was in part because they had not really very good information about the properties of the gas in here. So they thought the gas was maybe on the order of hundreds of degrees above absolute zero rather than tens. So they were off by, a factor of 10 on the temperature. They didn't really have good estimates for the density. And they also were just wrong on the chemistry. So they did actually look at, for instance, atoms that's themselves coming together to join molecules rather than going through what we now know as the kind of proper interstellar chemistry. So about a decade later, there was the first observations in the ultraviolet, and I'll mention in a few slides how that kind of worked. But the field of astrochemistry didn't really pick up and start to accelerate until radio. And so in the first detection of a molecule from the radio is shown at the top of this molecule OH. And then in 1970, there was the first detection of carbon monoxide. It's also one of my favorite papers because it has an abstract, which is one sentence, which is absolutely wonderful. It's the best abstracts that I've ever seen. And after the detection of carbon monoxide, there was really an explosion in astrochemistry because carbon monoxide is so bright. Basically, anywhere we look at where there's any sort of dense cold gas, we start to see carbon monoxide. And we see carbon monoxide within our own galaxy. We see carbon monoxide even at some of the furthest galaxies that have been detected away from us. So since that first horrible prediction by Eddington, there's now not just been a few molecules, but over 200 molecules have been detected and confirmed in the interstellar medium. This is a table that is kept here in Cologne. From the QR code will take you to this table. It has all the nice little links on there. And you see that astronomers have detected basically anything from simple molecules with just two atoms, the simplest one being H2, or just two hydrogen atoms, all the way up to very complicated molecules and complicated organic molecules, and even things like fullerenes. And as we're going on, astronomers are continuously detecting more and more of these molecules over time. So there's still a lot that we can do, and a lot that is basically being advanced in this field. One thing to note is that astronomers, when we talk about complex molecules, we're talking about anything that has 6 atoms or more. And basically anyone who does work in chemistry or biochemistry will kind of laugh a bit at this because it's very, very simple compared to what they do. But for us, 6 atoms complicates things enough, much less things like proteins. So for us, we just stay with 6 atoms. That's complicated enough. So before I talk about how we detect these, it's worth talking a little bit about all the different wavelengths of light. So we detect molecules really from submillimeter wavelengths, which is in the radio regime, all the way up to kind of ultraviolet. And this is a pretty great map from the European Space Agency showing across the spectrum all of the past and upcoming facilities that observe in those wavelengths. And some of these, for instance, are kind of brand new, like Cheops, and other ones like Athena are in the early stages of preparation. So they show here, for instance, tentative launch, for instance, of 2031. So pretty far off in the future. There's a lot of cool, exciting things that we can start to look forward to from a lot of these new telescopes, in particular James Webb, which will be launching later this year. And they just announced, I think 2 days ago, the very first James Webb Space Telescope proposals, which were accepted, which both excited and disappointed a lot of people. But I think there's a lot of great science that'll be coming out quickly from James Webb. So I'm going to take a bit of time to talk about how we observe molecules, because this is a question that I get quite a bit, where they say, well, you have molecules. I mean, people can kind of understand how we observe stars because we can see our own sun, but how we detect molecules is not always straightforward. So the very first way we detected molecules was actually the hardest way to do it. It just happened to be the instruments that we had at the time, and that was through electronic transitions, or really transitions involving an electron, and these happen in the ultraviolet and optical wavelengths. And I've shown up on the top left a little schematic of an atom of hydrogen, just because it's a lot simpler to show than a molecule, but it's in principle the same thing. So in this case, you have an electron at different energy levels, showing 3 energy levels here. When it's at some energy level, it takes some amount of energy to put it up to that level. And the universe, being naturally lazy, if it can, it'll drop back down to a lower level, and when it does so, it emits light. Now, the opposite thing can happen, which is what's shown at the bottom, where you have some bright background light source, and it shines through a cloud, and any light that is at this very specific wavelength will be absorbed and help push the atom or the molecule electron up to a higher state. Now, these absorption measurements are actually very, very sensitive, allowing us to detect very diffuse regions of gas. But they're also very hard to do because, for instance, in the ultraviolet, you have to go up to space typically to do that, or at least very high in the atmosphere. But these were kind of some of the first ways that molecules were detected. And I show in the figures here kind of 2 very particularly important observations. The top is the first detection of H2. H2 is the simplest molecule, but its simplicity actually makes the chemistry of it very complicated. But what we see is that you see all these kind of like divots in the spectrum, and those are caused by those wavelengths of light basically moving the electrons up to those specific levels. Similarly, on the bottom, you see this is the first detection of N2. So in general, very symmetric molecules make things very complicated. And so really the only way to detect them is in the ultraviolet or in the optical using this method, which means that, for instance, N2, being a very simple molecule, wasn't actually detected until 2004. So, almost half a century after the first detections began. So we also can observe molecules when they vibrate. So now I've shown kind of up in the top left, CO, so a carbon and oxygen molecule, and the vibration happens when the molecule vibrates. And on below, this is a laboratory measurement of what the vibrational spectrum looks like when you basically excite carbon monoxide in a laboratory. Now, those vibrational transitions take a bit of energy. So these transitions happen in the infrared. And so on the top right is an infrared spectrum from a massive young stellar object. And you see, again, all of these big divots. And this is caused by vibrational transitions from ices. So when the molecules are locked up in ice, they can't really rotate, they can't wiggle, but they can vibrate a bit. And so you end up seeing these big transitions where it's, again, an absorption. So it's looking at basically light that's been absorbed by the cloud material. You can occasionally see these vibrational transitions in emission. And this happens when you are able to warm up the gas enough to allow the molecules to start to vibrate. And that's what the spectrum on the bottom right shows. You see all these emission lines. This is in the infrared. And it's from an object that's being irradiated by a star. So basically it's getting warmed up, and that's allowing the molecules to start to kind of jiggle around. One of the kind of exciting things that James Webb Space Telescope will be able to do is it will be able to measure the emission from H2 as it vibrates. And it's one of the easier ways to observe it, because you're observing it in emission. And so there's a lot of planned proposals on observing the warm H2 in not only in our own galaxy, but in other galaxies as well, to understand how much of the gas there is in molecules. So finally, we can also see molecules when they rotate or other transitions, which I'll mention here in a minute. Again, we have our CO molecule, and it can rotate. In quantum mechanics, just like with the electron, says it can only rotate at certain frequencies. But this gives us also a lot of information when you have molecules that are emitting, because as the molecules move, you have Doppler shifting. So that gives us information about the velocity and the dynamics of that gas. So the figure you see on the bottom left shows a few different examples of this. So for instance, in the first case, you have basically some light that's leaving from this, but the molecule is moving up and down. But we don't really see that. However, if it's moving a little bit towards us or a little bit away from us, the spectrum gets blue shifted or red shifted, depending if it's moving towards or away from us. Similarly, if the gas is undergoing a lot of different motion, like if there's turbulence, or other sorts of motions, like if it's a disk that's rotating, you'll have all of these velocities added up, and that gives you some spectral feature. And so astronomers can measure not only the total amount of light, but also the shape of it, and that tells us the dynamics of the gas that where the molecule is coming from. And in general, the radio spectrum of a lot of the regions in the Milky Way where stars are forming are very bright in these emission lines. And so if you look at the figure that's on the right, you see at first it's a spectrum across from 330 gigahertz to 365 gigahertz. So this is in the radio, around 1 millimeter. And you see all these lines, and there's a lot of them. And the next one actually zooms in a bit. So now instead of looking at 30 gigahertz in total, you're now looking at 3 gigahertz. And again, you see just a bunch of lines. You can't actually see the structure of the lines. And only when you really zoom into less than a gigahertz across the whole thing, do you start to see all of these different lines. And in this case, a lot of these lines that they're seeing are at transitions where you would expect emission from complex organic molecules. And this is something that you see particularly. There's a well-known survey from the Orion KL region, which people have been digging into those lines for decades, and all of the lines still even don't have confirmed estimates of what it's coming from. So these kind of line surveys give us a huge amount of data and show us basically what all the different molecules are in that region of space. And when I said the other transitions, as you start to get the more and more complicated molecules, they start to kind of wiggle around a bit. Ammonia, for instance, is 3 nitrogen atoms in a little triangle with a hydrogen atom, and it can like flip around. So you end up getting flip transitions. And so as you get more and more complicated molecules, you get all these different ways that it can be excited and then emit light as it decays back down. And that's why if you see in this bottom figure, the molecule CH3OCHO has a bunch of different lines just in this one little window. It's just a bunch of different ways that the molecule kind of wiggles around and moves around. So there was a recent good review by Brett McGuire, who basically looked at the past century of astrochemistry and all the different detections, and had a few really great plots for this. So the figure on the left shows the cumulative number of detections of molecules. These are kind of confirmed detections of molecules since the very beginning, so around 1937. And as you see, it's kind of very slow for a long time, and then it all of a sudden explodes. And this is because of radio. And you see he annotated on there all these new radio facilities. And you see basically every time there's a new radio facility that becomes bigger or better instruments, there's kind of an explosion of new molecules that are detected. And in general, most of the new detections are coming from single dish telescopes because they're able to bring in a lot of light. And so you can sit them on an object for a long time. But things like ALMA have also revolutionized this because they can zoom in on regions and detect molecules that might only emit from a very small region of space. We can look at this in terms of how complicated the molecule is. And one of the things that is quite nice is that even almost a century later, we're still detecting simple molecules quite a lot. And in fact, most of the molecules that we're detecting nowadays are still simple molecules, kind of 2 or 3 atoms. So even though these things are the simplest, we're still learning a lot. We're still discovering a lot of them. And in particular, now we're starting to observe more molecules of things like argonium, which is an argon and a hydrogen that's ionized, and other kind of interesting, quirky molecules in space. And then on the right, this is a histogram of all the different detections of the molecules, and in which kind of region of the electromagnetic spectrum that detection was in. So what you see is that, for instance, the ultraviolet and the optical range, for instance, we only detected new molecules there that were simple, so 2 atoms. But what you look at then is in the millimeter and the centimeter, we're detecting things that are not only simple, but also complicated to 12 or more atoms. So I also want to briefly talk about how we model the chemistry, and really how we study the chemistry in terms of the actual chemistry itself. And so typically we like to visualize these in terms of the networks. So on the left are 2 networks from the Hollenbach and Thielen's paper, which was kind of one of the most seminal papers on astrochemistry. And these networks basically show the chemistry of very simple atoms for carbon and oxygen. So these networks were basically developed mostly to explain the emission of carbon monoxide. And when we look at these, we can start to understand the chemistry. So you can start, for instance, with atomic carbon, and you want to say, okay, how can we get carbon monoxide from atomic carbon? Well, one way is we can go and add in OH and get carbon monoxide. But that involves 2 neutral molecules, and so it's not particularly efficient. But one thing we can do is we can ionize the carbon to get C+. That can interact with O2, and that gives us CO. And so basically, theoretical and laboratory astrochemists build up these networks of basically all the possible different ways that we can build up these molecules, and then use laboratory and theoretical calculations for how often that reaction would happen. And we can also then zoom in on specific species. So the figure on the right is from a very recent paper. And this just shows basically the 3 major pathways to form HCO+. And so you see that this was actually a really brilliant visualization of this that showed that there's basically just 3 major formation pathways to get this molecule HCO+, which is a very reactive molecule on Earth. And that of these 3, there's kind of 2 main branches of this. So once we kind of know in general how this might happen, how do we model the chemistry? And unfortunately, this means we have to do a lot of the math for it. So for instance, if we just wanted to look at the amount of this molecule H3+, which chemists, for instance, would see as a very bizarre exotic molecule, again, it's very reactive, you would say, okay, the amount of H3+ that is gained or lost over some time is equal to, and we can kind of look at the network here and we say, okay, it is formed by having some amount of this of H2+, and then it's destroyed by interacting with carbon monoxide or N2. So we kind of get an equation that looks like this. And then you have to do this for every single molecule you want. So modern astrochemical networks might have 300 of these or more equations with 3,000 reactions. This is something that I don't think any human can do by hand, but luckily we have computers. So we basically build up these networks, and now there's been some sophisticated computational tools where we basically give it the network and it does everything for us. So we give it the network and it builds up all the equations for us all nicely, so we don't have to do it ourselves. The other way that we can do this is through kind of directly simulating the molecules, and this has been done more recently for ices. And so these are two simulations from Rob Garrett's group at the University of Virginia, and he's an expert in simulating how ices form on the kind of dust grains in space. And so in this case, he starts off with just some sort of dust grain and just lets things like water freeze onto it and carbon monoxide freeze onto it, and then those react. And you end up building up these layers of ice, and you end up getting this kind of big fluffy ice grain. And so this is mostly water ice. And what his simulations have shown is that the ice that we get isn't kind of ice that we think about on Earth, where it's, you know, kind of nice crystalline ice or snowflakes. It's kind of fluffy and amorphous and doesn't really seemingly have a clear structure.
Brandt, you have 3 or 4 minutes.
Okay. So what does the gas tell us? So this shows us the Horsehead Nebula in the optical light. And as you see, basically each different molecule shows a different region of this nebula. So that's because each molecule is sensitive to its own temperature, its own density, to the amount of radiation in there, and so on. So we can kind of learn about the environments within this by looking at, say, the Horsehead Nebula with all these different molecules and kind of piecing together the puzzle. So we'll kind of skip through this because it's also Horsehead Nebula. So now, you know, kind of the build up to prebiotics. So everything I've talked about are kind of more simple molecules. And so here we have a survey. The continuum source shows that basically they're looking at a core where a star is forming. So it's kind of warm. And the emission that you've seen in most of these panels are complex organic molecules or prebiotic molecules in the top 2 rows, or kind of more simple molecules in the bottom. In the square is the emission from the molecule formamide. And formamide is particularly important because it's a central link to prebiotic chemistry. So formamide is found in the chemistry for amino acids, for sugars, for nuclear bases, almost everything in our biology. Formamide kind of sits in the center of that chemistry. And we can look at basically a lot of regions in space, almost anywhere we point a telescope to a region that is forming a star, and we see complex organic molecules. So on the right, these are spectra emission in the radio of the emission from a large range of complex organic molecules, including, for instance, ethanol, which is an alcohol, and ethanol, and methanol. So basically all the anols and enols and stuff like that, and methyls. And there's also been a new survey, the Seeds of Life in Space survey, SOLAS, which has looked at these prebiotic molecules in a large range of sources, from kind of low mass protostars, things that would become things like our sun, to very high mass systems. So things that would become analogs of like Betelgeuse or something. And basically everywhere we look at, we see organic molecules. They're just everywhere. Again, this is towards a solar type star, so something that will form into a star like our own sun. And this is the first detection of Glycolonitrile. I only know the names. The chemists can tell the names much better. And this, again, is a very important prebiotic molecule that is kind of in the build-up to biochemistry. And in this case, this was a pretty firm detection. They had not just 1 or 2 lines, but they had just over 10 lines. So it's a pretty firm detection in this case. Also pretty recently, we had the first detection of a Chiral-Molecule. So on Earth, all of the chemistry in life that uses a Chiral-Molecule only uses one hand of the molecule. So a Chiral-Molecule is one that when you flip it, it's not symmetric. So the example is shown here. You flip it and it's not quite symmetric. There's something that's a bit off about it. So why life seems to favor one hand versus the other hasn't really been known. And this work by Brett McGuire in 2016 seems to indicate that in space itself, due to the radiation, it's selecting one of them. So I also want to talk about Rosetta. So this was, they directly measured some of the molecules on this object, and they found glycine, which is great, which means basically the building blocks to life are there in the solar system, available so that if they hit onto a planet, for instance, it can seed it. And finally, I just want to briefly mention laboratory chemistry, because as astrochemists, we really rely on our laboratory folks. This was a recent work from 2017, in which they basically built up ices in the laboratory and irradiated it with ultraviolet light. So their equipment is shown in the center there. The kind of idea of what they're trying to do is on the left. So they're irradiating some ice, and that basically injects energy and allows the ices to become processed and form other molecules. And what they found is that when they irradiated a mixture of methanol ice and this HNCO with ultraviolet light, the end product ice not only just had the original ices, but had a wide range of other pre-biotic materials. So this is work that is being done in the laboratory to directly try and simulate what's going on in the ices in space. And from these observations, they can start to understand and pull out what the chemistry is that's going on in space from the laboratory. So if you're someone who loves astronomy, but you also love tinkering in the laboratory, astrochemistry can be a great way to do that, because you can do laboratory astrochemistry, and not only will it be, quite impactful, but the astronomers and the observers and the theorists will absolutely love it, because we need laboratory measurements desperately. So thank you. Any questions? And I've left up links and QR codes to 3 different kind of astrochemistry sources for news or other talks.
Thank you very much, Brandt. That was very nice. It's a lot to cover, all of astrochemistry, but I thought that was very, very nicely put, and wonderful introduction. So, yes, anybody watching, please post any questions you have. We can talk about them right now, and we can ask the expert as we have him. I think anybody else in the committee, do you have a question?
Yes, a lot. First of all, let me say hi to our audiences, and then thanks, Brandt, for talking about this very interesting topic. I know you had a lot to say, because you're actually talking about a branch of astronomy. And I know that a lot of details are hiding there. So I'm curious about some stuffs. And the first thing that I would like to start with is that through your talk, you talked about complex organic molecules, and very early on you said that it must be funny for chemists when we call the molecules of having more than 6 atom complex ones.
Yeah.
But it's also of my curiosity that although we have detected some molecules like C16, or we know that PAHs are there in the interstellar medium, but still we have kept these nomenclature. Is it because C16 or PAHs are not organic molecules, or is it because we are respecting our pioneer scientists?
So I think there's a bit of both. So in some sense, the nomenclature of complex organics is just kind of historical nomenclature, but a lot of it too is that the chemistry is a bit different, or at least it's thought to be different. It's a bit unclear, and some recent observations might throw a wrench in this. But at least historically, it's been seen as the chemistry of PAHs and the physics of PAHs and things like C60 is different than the chemistry of things like methanol or other or some of these other molecules, where kind of historically the idea of PAHs is that they were formed around dying stars, for instance. Although some new observations might be throwing a wrench into that idea. But in general, I think it was also held separately just because it's been largely thought that the chemistry is separate. So it's been dealt with by separate groups and in different codes and things like that.
Ah, okay, good point. Then it shows that there are a lot there about how molecules are forming in the interstellar medium, or maybe also in the medium between galaxies. So it was a bit maybe confusing that in some slides we were talking about molecular gas, but then when it comes to the formation of molecules, we talk about the ice. Can you a bit elaborate on that?
Yeah, so let's take an example here for the Horsehead Nebula. So astrochemists tend to love the Horsehead Nebula because there's kind of where the star is kind of parallel. So we have like, it's almost a good example of like a one-dimensional thing. So it allows us to directly compare to simple models. And it's very rare, for instance, that the universe gives us like a nice 1D geometry. And so when we talk about the gas being composed mostly of molecules, in general, that means that the hydrogen is in the form of H2. So that's because hydrogen is the main constituent of the gas in the universe. When that goes to H2, we say that its phase has changed. In terms of the ices then will happen basically on these kind of dust grains, which the dust grains are kind of, in some sense, very similar to what we have on Earth, the kind of silicons and carbons and, things like soot. And, if you've ever just like, if you have a fireplace, for instance, there's dust in there. And so as things get colder, if you start to get like water, for instance, well, water freezes pretty easily. And so it'll start to freeze onto these dust grains. And then, so you have both kind of the gas phase chemistry going on and the ice phase chemistry. And those two also interact a bit. And so you typically then have more sophisticated astrochemistry models have not only the gas phase, but also the ice phase, but it's all still chemistry.
Ah, okay, nice.
A question from a viewer. It says in the talk it was mentioned that there was rotational transitions. Mm-hmm. However, how does that happen? How do they get these rotational transitions? Because aren't they just floating freely in space?
Yeah. So in general, as I mentioned, in general, the universe likes to be kind of lazy. And so, yeah, like a carbon monoxide atom will just be sitting there chilling. Sometimes, for instance, it might receive a little bit of light and the light has energy into it. And if the carbon monoxide molecule absorbs the light, it can impart some amount of energy into that. And what quantum mechanics says is that, the different ways that a molecule, for instance, or an atom can be excited are quantized. And so if it's a low amount of energy, the lowest energy thing that it can do is, instead of vibrate, is just start to rotate a bit. Or another way that it can be excited is through a collision with something else. So a collision, for instance, with hydrogen, with helium, with an electron, basically with anything that is abundant can collide with this and impart some amount of energy into that. And that allows it to kind of get excited and start moving. But in these regions, the gas is very cold, so it doesn't like to do this movement. So it'll eventually just decay into that kind of low, lazy state. And when it does so, it emits light.
Any other questions?
Brandt, serious question. Do molecular spectra need QR codes? Because I just saw one of your slides and there was a QR code. At first I thought, like, why just one for all of these molecules? But I guess could be a good idea for a PhD, but I don't know. What do you think?
I'm trying to think of where that was. Was that here?
No, before this, because there was this huge list of molecules.
That was the CDMS.
Yeah.
Yeah, so this actually links to the Cologne database. this just basically gives you a link to this table. But it is worth noting that at Cologne is basically one of the biggest centers for measuring a lot of the properties of these molecules. And we also host in Cologne the database, which a large number of astrochemists around the world use to get a lot of the data for their astrochemical models. So there's a lot in astrochemistry, which is done, of course, through Cologne. Cologne's one of the kind of world centers of astrochemistry, from observations, theory, and laboratory.
That's good information. I had my I mean, I feel a bit proud of Cologne now, and I wish I had my sunglasses. But thanks for telling us that. What do you think is the role of dust in all of these detections? Because sometimes the dust combines with molecules in space and can get complicated separating the spectra, right? What is your view about that?
Yeah, so it depends a bit on the wavelength regime. But in general, for instance, in radio, you have dust emission, and then you'll have line features on top of that. So the dust emission then will basically act as something you have to subtract away if you want to get to your line emission. In the optical and ultraviolet, you end up having a problem where you need a background source in order to observe the absorption. But because of dust, you can't actually, it's very difficult to observe these molecules in absorption deeply embedded in the gas, because that would mean that you have a star that's also basically the light has to go through all of that, and the dust blocks all of it. So for instance, the molecule H3+, which is one of a very important molecule for determining a few different parameters or a few different characteristics of the gas, is observed through absorption in the infrared. And for a long time, and still to this date, most of the observations of this are in the kind of diffuse regions, with only a few observations of H3+ in the dense gas. And those were in very niche cases. So because of the fact that the dust absorbs all this light from background sources, it greatly limits our knowledge and our capabilities to observe these molecules in absorption throughout the cloud. We're basically constrained to just the kind of the diffuse regions.
So, but this is good to know, and this is largely about the extinction that is caused by the dust, right?
Yes.
But do you also think it causes problems with the dynamics of the molecules themselves? Does it have any effect on the rotational and vibration spectra of these molecules that we want to detect?
So there is a bit of work on this. In general, so the amount of dust to gas by mass, the dust mass is typically around 1% of the gas mass. So there's still a lot more gas than dust. However, the dust does facilitate the formation of a lot of chemistry, including H2. And without H2, you really don't get you don't get any chemistry. And so for instance, H2 forms on dust grains. And then basically when it forms, the reaction is exothermic. So it releases energy, and that releases it from the grains back into the gas. So it's the dust in that case plays a very important role in basically helping to start up the chemistry.
So it's good and bad.
Yeah, and so the dust for the chemistry, the dust can really act as a place for reactions as a catalyst, basically, basically a site. So in the case of H2, because it's perfectly symmetric, there's really no easy way to get two hydrogen atoms into a bound state in the gas phase just by themselves. But if they're on a dust grain and they can kind of diffuse and hop around the dust grain, they can come together. And when they react, then it releases energy, and that basically pushes it off the dust grain. And so this is a problem, for instance, when people are trying to study the chemistry of the kind of first generation of star formation before there was any dust. And this for a long time was a big problem of how do you form molecules at all when you're in a universe that has no dust. And luckily there's been a lot of advancements in the past couple of decades that have kind of given some possible ways to do this.
This is very exciting. I hadn't ever thought about early dust. And also I will remember the good role of dust when the next time I feel lazy about vacuum cleaning my room. because it's instrumental in so much exciting stuff. So let's see what it does here. Yeah.
Maybe I can follow on the point that it came just out of your discussion with Parrit. So it seems then it's very necessary to look back into the early universe environment to have a complete view of the chemistry. But at the same time, it was very interesting when you showed this Rosetta mission. It shows us that we have our solar system also inherit a lot of features from the early universe or the universe around us. So maybe you can also tell us a bit more about this.
Yeah, so I'm not a big expert in comet chemistry, but there is a lot of work that is being done within astrochemistry on trying to understand not only when comets form, but comets have a lot of ice on them. And so there is a lot of evidence that where the comet forms, for instance, within the disk around the in this case, for instance, the young sun had a disk around it that the planets were forming in. But comets also formed in it, and where it formed in that disk seems to have a strong impact on what is in the ice of the comets. And so there's now a lot of new theoretical measurements that are trying to do this, and having missions that can actually go and take direct measurements on comets is of course huge, because we can get much better and more accurate measurements to try and figure out how this works. And so astrochemistry really looks at the chemistry from basically not only the early universe, but all the way to the kind of the gas, for instance, in the Milky Way, to the solar system. So for instance, Titan atmospheres and exoplanetary atmospheres, and comets. So it's a big field with a lot of very interesting stuff going on.
Thank you.
Brandt, are you hiding aliens from us?
I am not. My flat's quite small, so I don't think one would fit. But maybe someone else with a bigger place is hiding all the aliens.
I mean, you could hide a little molecule, you know, like it's not that hard. Maybe in your lab.
That's true, but that might break COVID restrictions because we're from different households.
Oh yeah, I did not think about that.
Yeah, but Parrit, you point out to very important things that maybe in the very last slide, Brandt shows us these, let's say, different networks that may result into detection of pre-biotic molecules. But I'd like to say that we are not that close and we are not that far from this, because what we have detected so far in the interstellar medium are the sign of we possibly can detect prebiotic molecules. But we have not yet done that. So maybe Brandt, tell us a little bit more on that.
Yeah. So one of the downsides is as you get to more and more complicated molecules, they become harder to detect. In part because they become less abundant, so there's less of it to emit light, but also as they become more complex, there's more ways for them to become excited and thus more ways for them to lose energy. And so rather than, for instance, carbon monoxide has a small number of very strong lines because it basically rotates around in one way or it vibrates. But as you get to more and more complicated molecules, there's a lot more ways to do it, which means that that same amount of energy can get spread out over a lot of lines, which means that not only are you looking at less material overall, but each possible line becomes weaker. And so as we build larger and larger telescopes or start looking deeper and deeper, we start to see more of these. But this is a kind of a known problem. And as people are now planning for the next generation of radio arrays, this is something that they've looking at basis by saying, basically, if we wanted to detect, something like an amino acid or sugar or even just glycine in space, how deep do we have to go? How complicated, or how large of an area do we have to have for the telescope in order to observe this? And in general, a lot of these kind of first detections happen in kind of one or two different well-studied areas because they're known to be either rich in molecules or they're close. So the region, for instance, SAGB2 is heavily observed because it's known to be very rich in molecules. And it's also, kind of close enough that the emission is bright enough that we can go deep into it and observe it. So I think at some point there's just a limit on how complicated we can get to, just because, kind of physics is starting to hurt us at this point.
Yeah, so maybe then, although the progress of science is not linear, we need to ask Parry to be a little bit patient to find the audience out there.
I'm still sure they're in his room.
Okay, that was a nice discussion. Thank you, Brandt, again for the presentation. Very wonderful. It's nice to have a reference for astrochemistry. It's something that I don't do enough. Now we have the second section of our event, which is the presentation of Astro News by Harit. If you're ready to share.
Yep, right on, right now. I hope you see my screen. Do you?
Yes.
Okay, good. So after all this serious nerd chatter, as always, let's bring you the exciting astro news from this month. Big B's back, of course. You need to check out the new image from M87 star, which is the black hole. About 2 years ago, it got its first reveal because the first time a direct image of a black hole was taken was of this black hole. And it was revealed in 2019 on April 10. I'm not sure what you guys were doing, but I exactly remember where I was when that happened. Because actually, I was just watching the stream online, so of course I remember. But pretty exciting. Now the EHT collaboration, the Event Horizon Telescope, released another image of M87 star, which shows the polarized light that is detected on the same around the same black hole. Polarized light here points to the black hole's rings being a magnetized environment. The image is said to be cool, even though magnetic fields have been connected to hot jets emanating from the black hole. In fact, while certain space news editors claim to have reported like boggled minds on the day of the first reveal, we at AoT Koeln always knew the black hole would look like a donut. Isn't it, Craig? Because we saw the movie Interstellar. Yeah. I don't remember when Interstellar was. I think 2018 or 17. Anyway, so we knew. Yeah, we knew. Bottom line. It is also reported that by wearing polarized light sunglasses and looking in the direction of the black hole, you will not see this polarized light around the black hole, because I tried. And there is a bit of a date problem here, because dreams of a black hole day on April 10 have been smashed. I was really expecting the next reveal to be on the day of the previous reveal, even though it's 2 years later, but it could have been like the Olympics, you know. In fact, the dreams of a black hole month have also been smashed, because they didn't even care to like wait one more week. April 1st would have been kind of nice, but everybody would have thought this is fake. So, okay. Yeah, but there is NASA's Black Hole Week around the 12th of April, I think. So maybe you guys want to check it out. funny picture. Popular astronomy communicator Phil Plait. This is what he had to say about the picture. He said, "Oh, I wouldn't have thought this was possible." But what is that in the middle of the black hole? Let's zoom in. It is, of course, the ship that got stuck in the Suez Canal. That's right, guys. Not many people know that the ship that recently got stuck in the Suez Canal and blocked world trade for almost a week fell directly into the black hole as soon as it was freed about 2-3 days ago from the Suez Canal. True story. It is now said to block the black hole's Hawking radiation and is a serious obstacle in the black hole's weight loss journey. I hope that tells people what Hawking radiation does. This is very interesting, and I think it's also very interesting for Brandt and all of us. Complex carbon molecules were recently found in a molecular cloud. So this MIT team observed polycyclic aromatic hydrocarbons in the Taurus molecular cloud, which is kind of a cold place, colder than expected. It hasn't yet started forming stars as such, so it's still not expected to be the place where you want to find polycyclic aromatic hydrocarbons, especially because usually these molecules are detected in hotter places. Also, usually where stars have died instead of still waiting to be born. The researchers used the Green Bank telescope, which is the world's largest steerable radio telescope in West Virginia in the US. Let's just say PAHs are not just the byproducts of dying stars, but after this discovery, now we can think that they may also be assembled from smaller molecules without so much heat. This will obviously prompt a rethink of theories regarding what chemicals are available during star and planet formation. I was a bit confused about whether this was the first direct observation of a PAH molecule, or because I, along with all of us, we are aware that PAH molecules are usually detected in interstellar medium, as also clear from Brandt's talk. But I think it is the first time that they had a direct observation, in the sense that I quote this from an article. About 10 to 25% of the carbon in space is believed to be found in PAH molecules, which contains at least 2 carbon rings. But before this, the infrared signals weren't distinct enough to identify specific molecules. What do you think, Brent?
Yeah, so PAHs are very often observed in these kind of infrared bands, but there's, in general, then we those infrared bands are attributed to classes of PAHs, or kind of different modes of excitation within PAHs, but not the direct hydrocarbon itself. So this was the detection in radio instead, and then it was had a confirmed detection to a specific PAH and a specific transition. So that is the big thing, and it was using, of course, not only a huge telescope, but some a new, more sensitive survey and some newer kind of data techniques on how to pull out different signals.
Does it mean that this new detection tells us what atoms are in the PAHs? Do you mean that? It's clear what compounds we are looking into?
Yeah, so this was a detection of a specific molecule, or 2 specific molecules, I guess.
Yes.
Roya, the exciting part is that I got into a bit of a rabbit hole while reading about this, and I found out something called the PAH world hypothesis, which is similar to RNA world hypothesis and DNA world hypotheses. So just to say one more step closer to aliens, nothing big.
Yeah, I wanted to say that it's a kind of hope for you. We are getting closer.
Getting closer.
Yes.
All right, then we move on to something that is not aliens, but still kind of aliens, let's say. So possible connection of Oumuamua with exoplutos. I think you have heard of this little object that was found in 2017 because it was just casually floating by the solar system. People expected it to be a comet, but turns out it's not. So the new thing, so there have been studies going on to prove or not prove what it is. It is clear it is something that came from outside of the solar system. But now these ASU researchers say that Oumuamua was probably thrown out of a young star system about 500 million years ago. And the object does not exhibit usual comet-like behavior, which behavior was previously attributed to aliens in some really heated debates over the years. There were a lot of anomalies, notably one that it was closing in on the sun while traveling towards the sun. It was pretty fast, but pretty slow as compared to normal comets. But while moving away from the sun after the orbit, after a flyby, let's say, it was much faster than usual comets. So these are some anomalies that were observed. If this is true, by the way, that it is connected to Pluto-like objects, that means objects like Pluto, which otherwise will probably not be directly observed soon, like exoplanet Plutos. They have found a new way to say hi to us across solar systems. They just send a messenger, Pluto-like planets, because they know that they won't get footage normally. Because in my opinion, this is very exciting in a world which is very much biased towards hot Neptune exoplanets, because they're so visible and hot does not mean that we have to ignore these cute objects here, which sometimes linger at the end of solar systems. In fact, fun fact about nitrogen ice, which is thought to be the ice that is present on this object. Nitrogen ice can form glaciers, and most notable on the surface of Pluto, because the density of nitrogen ice is much more than water ice, which causes icebergs floating on nitrogen on the surface of Pluto. Imagine. It is exactly for this reason I vote for nitrogen ice as the best ice. Yeah, that's it. Because I mean, Pluto is underrated in the kind of phenomena it exhibits, and a lot of interesting stuff happening there. Also, because there's a lot of water ice form there, and there's a lot of mountains made of water ice there, which is unheard of in the solar system. So we need to get back there, I think.
Nitrogen voted, or you voted for nitrogen to be the most nice?
We voted, I think. Okay. Support me here, Roya.
Yeah. If I support you, then you cannot eat any more ice cream. I vote for ice cream.
Yeah, because you like liquid nitrogen more than solid nitrogen. I see where you're coming from. Because ice cream usually exists in liquid nitrogen. Yeah, I can understand your feelings, Roya, but think about it.
Yeah, I can do that.
This is a model, a picture from a model of how they expect this object to have entered our solar system. It started, they think, a long time ago, about 500 million years ago, as said previously. It was eroded by galactic cosmic rays and slowly entered the solar system. It will still be here until around 2040, according to these models. So we still have time to, send a probe on it or something and actually look for aliens. In fact, I read a book. I don't know if you know, if you guys know about it. It's called a book by Xixin Liu called um, I forget the name, but this book had a bunch of aliens, and the spaceship was exactly shaped like this, and they just entered the solar system, broke everything, and then went back. But this story has a really close connection to that story. I'm not ruling out any possibilities. Finally, it's a great pleasure to announce, but also not a great pleasure to announce that April 5, starting April 5 would be the International Dark Sky Week. I will explain why it's not a pleasure to announce, because sadly we have a very small number of places now where we can really observe the sky without telescopes, and it looks as dark as it should look in all its magnificence. But yeah, let us celebrate dark skies, let us preserve dark skies, and let us actually preserve the one thing that is not still polluted, at least in all places. And this is also important because these days there are lots of programs that threaten our view of the dark sky. SpaceX has lots of satellites going up to provide intel of us, and more companies are coming up. There's space debris, which threatens also to block the view to the sky. But I hope all of this will be better. If not, then I will have to write a proposal to establish radio observatory on the moon very soon. I hope you guys will.
Gross. Oh no.
Okay.
But yeah, I like this Dark Sky Week. It's a nice event to follow. They seem to have a lot of events around the world. So if you have a chance to go see one near you, then I would recommend it. I don't know if you guys have ever seen a dark sky observatory or just a dark sky in general, but I haven't seen one in 3 years or more, because ever since I've been in Europe, I've always been near light polluted cities.
Mhm.
Did you guys see anything?
Yes, sure. We have a lot of very dark sky in our country. And something which is very surprising for me is these days, even when we are walking outside, we can see a lot of very bright satellites from these maybe constellation satellites. But back 10 years back, when we were in the even very darkest, under very darkest sky, we could not see this much satellites. And it was a kind of match between me and my friend to find one.
Yeah.
Yeah.
But now it's going to be a bit different.
I think we have. Oh, sorry.
Go ahead.
We have also told the people who are living around Cologne in our, I don't know, third or fourth event, that if they are interested to look into the very dark sky here around Cologne, you can go to Eiffel National Park, and there we had experienced very dark sky.
I'll have to check that out. Sorry, Prerit, you cut out. I wasn't able to thank you for your presentation.
And you're very
interesting news. I like your image of the black hole, the new polarized light image. It's quite nice. I remember that day when that picture was first released, actually, our astronomy department, because we had a professor and a lot of people that work in EHT, we had our own, we had a little celebration, and then everybody watched the live stream in the cafeteria, I think. But It's quite nice.
Yeah, if we have a knowledge about these kind of events in the future before they happen sufficiently in advance, then we could sort of have we could coincide that with AoT events. You know, it would be nice to
Yes,
have
that would be
have a
wonderful.
good time. Yeah.
I think a few people had, a few other satellites of AoT had planned their AoT event to be like on the day of the Mars landing of Perseverance.
I wish, I hope and wish that we are back to that reality soon.
Yeah, so we'll have to plan our events a bit better, I guess. But yeah, I like the image of the new EHT image. It's kind of like it increased in resolution a little bit. Maybe
I think we are all in the institute in the.
Yeah, it is.
connection is off, I think.
Parry, you were saying something?
No. I'm just waiting for your comment.
Yeah, I was saying that day of this release 2 years ago, we were all in the seminar room of the institute, Cosmo room, and it was so exciting. We were all waiting for this breakthrough to be announced, and yeah, hope for again getting all together in person.
Yes,
in fact, do you guys hear me?
Yeah, sorry, go ahead.
Okay. Yeah, I had one of my great friends joining me who was not in astrophysics, and it was the first time that she had such a great historic event related to astronomy unfold in front of her eyes. And also for me, kind of, because even though we watch launches and all the big stuff all the time, this one was pretty era defining in that sense.
Yes.
Yeah. Good. Any other comments on the news? Maybe not. Okay. Well, thank you again for the news, and thank you, Brandt, for your presentation. That was wonderful. Quite enjoyed it. And yeah, everybody should look next week and see if you can find some dark sky conservatory, some event next week, and just enjoy the night sky while you can. Next month, we will be back with another event, this time with Stefano Evagazio, another PhD student here in Köln. We don't know what the topic is yet, but we'll let you know on social media. So thank you again to everybody who's watching, and thank you to our guest. And yeah, we'll see you next month.
See you guys.